Hello, welcome to another problem-solving session. Um, John Golden again. So I've got two geometry questions to talk about this time. So again, I'm going to try to think through them, do a think aloud like I would on a test, and then maybe some big idea notes to think about the understanding afterwards. So this one, we've got a picture there. That's usually the first thing I notice. Triangle, one angle's labeled 70 degrees. You can't go by the pictures kind of to assume like it's equilateral or it's isosceles. Instead, you have to read to see what kind of properties they're expecting. So this one says the length of sides AB and AC below are equal. And I actually want to make some mark on that. A lot of times mathematicians use these little mark, or you could write down information somewhere else, just jot it down. What is the measure of angle A? So this one here. Okay, so AB and AC are equal. So what they're trying to get you to access here are the properties of a triangle. Right, so a triangle with two congruent sides is isosceles. So kind of a what else do we know? Right, this is the thing in math a lot of times. Like I tell you one thing, what else does that tell you? So we know it's isosceles. That means we usually think these two sides are equal, but it also means these two angles are equal. Right? And then how could we get the third angle? Now they're asking us to combine that with the other big triangle fact, right? The kind of the biggest one is that if we add up all the angles in a triangle on a flat surface, we get 180 degrees. So 70 plus 70, that's 140, which means this missing angle must be 40 degrees to add up. So looking at the answers, here it is, 40 degrees, and we've got some distractors here. So they were trying to get you to think, oh, isosceles is the same, 70 degrees, so that's a distractor. 110 degrees is using the 70 plus what is 180. Not sure where the 20 comes from. Maybe that's an common arithmetic error. And 55 would be if you thought both these were the same. They'd have to add up to 110. So, so this is a tricky one because it's giving you all the different distractors that could come from kind of not paying close attention to which angles are equal, which sides are equal. Okay, so so just some kind of teacher notes on this. So because they're talking about the length is why they say equal, or they could have said the two sides are congruent. The 70 degrees is getting you to think about that 180 degree total. Hi. So we're going to talk about this problem, and it's actually the second time I'm going to be doing this because the first time I made a mistake. This problem is about the area of a triangle, and I used the wrong formula for the area of a triangle. So just kind of a careless mistake, but it was interesting because the answer I got was in there. So anyhow. This time we'll work through it with the correct formula. And okay, so we've got this problem, and first thing I notice about a problem a lot of times is the picture. So we see a picture here, we've got a triangle, we've got what looks to be an altitude, but notoriously the pictures in these problems are not to scale. And that's going to turn out to be the case for this one too. So reading the problem, in the figure below, ABC is an equilateral triangle. So I would not have guessed that. So what they're saying is that this length is the same as this length, is the same as the whole bottom length. So it's equilateral. The other thing that means is that each of these angles is the same. So each of these is 60 degrees. Okay. AH is perpendicular to BC. So this is an altitude. So an altitude or height of a triangle is always perpendicular because that's what gives the distance from a point to a line or a point to another object, is when we've got that perpendicular distance. And they tell us the length of it is 2 times root 3. And that might seem like a strange length to have, but it comes up in triangles a lot because of the Pythagorean theorem, right, that we get these square roots and lengths. What is the area in square inches? Okay, so, but units aren't going to be an issue. That's what they give us for the other information of triangle ABC. Okay, so we going to be careful with this time through, right? The area of a triangle, half base times height. Okay, do we know anything? Yes, we know the height. So it's half whatever the base turns out to be times this 2 root 3. Okay, so the only thing we have to find to know the area is the length of the base, this whole base. Okay, but we don't have any information to find that, right, directly. So we're not given the length of part of it, we're not given the lengths of one of the sides. All we're given is this length of the height. But we're also given this equilateral thing, so that is going to turn out to be enough information. So we know in here, if we just take this part of it, because that's an altitude and we've got this right angle, we've got a right triangle. And that means the Pythagorean theorem. Okay, so people tend to overuse this, right? So the Pythagorean theorem says that if we have a right triangle, if we square the length of one leg and square the length of the other leg, we get the hypotenuse squared. So in our case, this whole side of the triangle is the hypotenuse. It's also, because it's equilateral, the base that we're talking about down here. So I'm going to use letter B to show that. Okay. Well, you can use whatever letter you want. Maybe you could call it X or something, because the way you usually hear the Pythagorean theorem is a squared plus b squared equals c squared. But those are just standing in for whatever values we're talking about here. So on second thought, so as not to confuse myself, I'm going to call this length x. Okay, so x in this case is the hypotenuse. So that's an x squared. And when we're looking over here, we're going to be looking, that length x is what we're going to plug in here. Okay, so what are the two legs? Well, we've got this leg, 2 root 3. And we've got this leg, which is just part of it. Right, so we're looking for just this part here. And what do we know about it? We don't know how long it is compared to here. Although actually another way to do this problem, we could use some trigonometry, because we know this is a 60-degree angle. So we could use the fact that we know this length to find this length by using the tangent that relates the opposite to the adjacent. But let's stick with the Pythagorean theorem here. So whatever this length is, it's half of the whole side. The whole side is x. So this part we're looking for is just half of x. You've got to be careful about where the squared goes. It's not x squared divided by 2. It's x divided by 2, that whole thing squared. So if we square these two parts, when you square things that are multiplied together, everything gets squared. So 2 squared is 4. The square root of 3 squared is 3. That's what makes it the square root of 3. So that's 12. And here we square everything multiplied or divided. So we get x squared 2 squared, so x squared over 4 is equal to x squared. Okay, so we want to solve for x. And you might be thinking quadratics, but there's no linear term, so I think if we get all these together, we'll just be able to take a square root and solve it. So the 12 is x squared minus x squared fourths. So you could think about that like, well, okay, so that's 1x squared minus a fourth x squared. Or you could get a common denominator and subtract it that way. However you're comfortable thinking about this. So 3/4 x squared. So 12 is that. So we want to get rid of the 3/4. So you could either think about multiplying 4/3 by each side, or you could think about dividing by the 3/4, whichever way is more comfortable. There's always more than one way to do these things. So 12 divided by 3 is 4. 4 times 4 is 16. So x is plus or negative 4, but we're talking about lengths, so we're going to forget about the negative 4. So this triangle that we started out with is 4 by 4 by 4, which means the base that we're looking for, the base of the triangle, is also 4. So we get a half times 4 times 2√3. So a half of 4 is 2. 2 times 2 is 4. So we get 4√3, and it's part C. Okay, so we've got fresh slate. Well, what if we couldn't remember all that stuff? That was pretty complicated what we did. We used triangle properties, we used Pythagorean Theorem, we had to solve with algebra, and then we had to go all the way back to the area formula. Could we do this one by just using kind of process of elimination? So, or say you couldn't remember, or you got uncomfortable, or you got stuck. This is always a way to think about going about it. Okay, so what we're given is this length of the altitude. So however long this is, right, we know it's longer than this length, because this is a slant from here to the opposite side, and this is that perpendicular shortest distance. Okay, so whatever that base is that we are looking for, it's got to be bigger than this value. Okay, so they're saying these are the area. So if this is half of something times 2√3, we could figure out what that something is to make this be equal to 12. Right? So, well, to get rid of the √3, we'd have to, I think, do a √3 in there. Maybe that's not the quickest way to go about it. Let's just do 12 divided by that other stuff will be equal to our blank. Right? So 12 divided by half of 2√3. 12 divided by √3. Oh, yeah, whichever way is easiest for you to think about. So this √3, the thing to remember is that it's always √3 times itself is 3. So, so we could think about 4 times 3 divided by √3, which is 4 times √3. Okay. So is this side double this side? Well, that seems kind of unlikely to me. But it is at least possible, because it's bigger. Okay, so what about 2√3? So if that was equal to half of something times 2√3, well, to be the same, this would have to be 2 here, right? So half of 2 is 1 to get 2√3. And 2 is too short. We need something that's longer. So that is right out. 4√3, that's the one that on the other one we found out we thought might be the answer. So if we think about that, that's half of something times 2√3. Well, this is 2 times the 2√3. So this would have to be 4. So 2 times √3, if you check it on your calculator, is around 3.4. I think about √3 when I'm estimating is 1 7/10. So 3.4, a little longer than that, 4, that is very promising. Right? So 4√3, that's going to be bigger, that's going to be like around 7. Okay, that seems too much. That's that double the length. Okay, so 8√3, oh, well, to get twice the area, it was going to have to be twice whatever this was. That's 8. That's even bigger than this other one. So if we were just guessing, even this is the best guess, right? Because with this length of 4 seems the most possible for one side. So even if we couldn't remember connect or got stuck in one of the parts, this 4 for a base is a pretty reasonable guess, and that would give us this part C also. Okay, interesting problem. This was a complicated one, so I'd love to hear what you think about it or how you solved it. And also, remember, we got the 2 problems from Jordan, and we're looking for problems to do, right? So if you have some problems that have come up in your practicing, please go ahead and send them to me, and I'll give them a go. And if I get them wrong, I'll try them again. So that's what we've got. Thanks very much.